Hi everyone, thanks very much for joining today's webinar where we're talking about Siemens Simcenter Inspire Cast and some of the other tools available within the Siemens portfolio to hopefully allow you to deliver more value to customers. There will be a recording available post-event should you want to share that with colleagues. So I'm Rob and I look after the sales and marketing side of Origin, and we'll be hosting the session today as well as providing an introduction. Really pleased to be joined by Tim, who heads up our support and training functions at Origin, and we'll be focusing in on the casting simulation tool in particular, covering a design to simulation workflow to help you understand what's possible within the portfolio of tools. By way of agenda, runtime just under 60 minutes. We'll leave some time for questions towards the end, so please feel free to put your questions in the chat and we'll make sure we get to them. As I said, short introduction from me, including some detail around the acquisition of Altair by Siemens and what that means for customers. I'll also talk about the portfolio as a whole and what opportunities are available to move beyond casting simulation in order to differentiate yourselves in the marketplace. I'll then discuss AI before passing over to Tim to provide that demonstration for you. So Origin are an official Siemens partner, and we've got the highest concentration of casting customers globally for Siemens. We're focused specifically on manufacturing simulation tools, and whilst Inspire Cast in general is a newer tool compared to some of the other tools on the market, we've certainly seen steady adoption over that time, where we now support about 15 to 20% of UK foundries with casting simulation tools. We work with Siemens because we believe in terms of initial investment and really encouraging widespread usage of simulation across the organization, we believe Inspire Cast fits that bill. More importantly, I believe the world has moved on. It's not enough to be doing casting simulation. This is the bare minimum, and all of your competitors are doing this as well. What the Siemens portfolio allows you to do is bring other services to market, all whilst using the same license, which we think is really important. Having come from Altair, we already know their strengths. Early on, Altair invested heavily in manufacturing simulation in addition to optimization. They also saw the importance of AI and data analytics very early on, which all things combined provide a comprehensive toolkit for the manufacturing workflow. With the Siemens acquisition then, we now have access to more robust CAD capabilities in terms of Solid Edge, NX and NX Essentials. Furthermore, Siemens have dedicated solutions for shop floor automation, and that's not something that we had previously. They also have proper product lifecycle management. Specifically for our casting customers then, we have the ability to provide CAD tools if necessary prior to a simulation, in addition to expanding the scope of what we can offer to start thinking about the shop floor. And this too lends itself to AI when we talk about that shortly. Without going into too much detail, we've also seen aggressive development as we start to achieve parity with the other tools on the market, which have been around much longer. But we've also worked hard to try and differentiate our approach by introducing flexible mesh approaches, introducing specific modes to allow simulation to be done much quicker, and also to allow for optimization, experiments, and dealing with the product performance post-cast, essentially closing the loop and offering more before and more after the casting is produced. So if we tie that back to some of the things that Tim is going to show and look at a casting workflow, then we start with a model. Here, we might use the built-in tools within the casting simulation tool to clean up geometry, or we might use a full-blown CAD tool, which we can now offer, such as NX Essentials. We could then use built-in FEA tools to check the design part's performance and also potentially offer new services to customers focused on looking at the part that they've sent over and looking at opportunities to optimize that part to reduce weight and save on material usage, also while making sure the method is still going to work and we still achieve similar strength targets. We could then look to validate the stresses on a part during manufacturing to show any problems in performance post-cast. Again, an integrated approach. We design, we optimize, we validate, we iterate, all in the same platform, all under one license. Now, finally, one question that I would have is, what are we doing with all of this simulation data? How are we connecting that back to what's happened in real life? Well, in general, what's currently happening is nothing. So you've got all of this production experience, all of the simulation data, which isn't really doing a lot for your organization. And this is where AI comes in. It's not magic. We need three things: data democratization. In plain terms, this means giving people more access to data, giving more people the opportunity to contribute to that data. Linked to that is an organizational shift mindset. And most importantly, a software partner that actually has the tools to make this happen. So we see a lot of hype around AI. You always see the end result, and it often looks magic. Looking specifically at a casting organization, then, I've broken up the silos of data, or places which you might have data, into three core pillars. We've got corporate data, which would contain information about customers, meetings, quotes, finance information, billing, that sort of stuff. We've got operational data, which might hold information around machine performance. It might hold information about quality issues. And then finally, we've got simulation data, all of the data that you're accumulating through those simulation runs. So we've got three silos of data there. AI really can do two main things. It can answer questions based on available data, and it can trigger business processes if we provide access. We've all asked ChatGPT a question. It's not as magic as it sounds. You ask what the weather is, so the model looks at its training data and, where necessary, searches live sources such as the internet to return the answer. It's great because it's much quicker at reasoning than we are. For example, if you sent a spreadsheet of 1,000 customers with job data, it would very quickly be able to tell you who's the most profitable. If we had sensor information from all of our machines and we were constantly sending data back to our AI model, that model would be able to interpret that data very quickly, something that the human brain just simply couldn't do. So we could say, based on live data, email me or notify me when you think there could be a problem with a machine. We could then go a step further and potentially feed back into the model to say, you told me this was a problem, and yes, it was, or no, it wasn't. And by doing that, the model will learn and improve. If we take simulation data as an example, we could use the same approach. We could link production data to the simulation data. So we could start to look at, well, this particular method had a very low scrap rate, as an example. So when we then go to do future simulations, we might be able to draw some similarities and get some answers in terms of what the best method was. So what's the pattern? Well, it's just data, really. That's it. There's no magic behind it. All it is structured data. And the more you feed it, the more opportunities you've got. So what I'm getting at is, for many foundries, probably a lot of work to be done. It's not reasonable to expect that your corporate production data and simulation data is all in one nice central database ready to be fed to an AI model. It would be nice, but it's unrealistic. What we need then is software tools or a data layer that's able to connect data from multiple data sources, make sense of it. Without that, you'll always struggle leveraging AI. And in a lot of our conversations with customers and prospective customers alike, tells us that they still rely heavily on paper-based production processes to track quality issues. Perhaps customer lists are in Excel or in someone's head. Quotes are scattered around everywhere. Simulation data goes into a black hole, never to be seen again. And this just isn't conducive to leveraging AI. And there's no doubt that your customers are expecting things faster, less mistakes, and overseas companies are offering things at a lower price. But here's our opportunity. We have decades worth of knowledge, decades worth of quality casted parts and the know-how. We just need to start leveraging this experience to make us faster, more efficient. And that is where AI comes in. The final word on this, it requires cultural change, as I mentioned earlier. It's not good enough to have one person running simulations. Usually, it's down to the fact that your casting software is just too expensive. But really what we want to be doing is expanding usage, reducing it, locking capabilities away. You need people contributing to your data so that your AI model can learn, so can your organization. You need to look hard at the integration of workflows, the integration of data. And through the Siemens portfolio, I think we can help with that. So many of you on the call today will, of course, no doubt be using simulation software. May well be happy with that. I guess what I'm suggesting is that casting simulation is great, but the new wave of innovation is undoubtedly around AI. So you should be asking your vendors, what tools do they have available to actually make sense of and reason about your simulation data? What tools do they have to connect those different data silos that I mentioned on the last slide? Because if they don't have a strategy, you're very unlikely to be able to leverage AI. So a few examples quickly. These are based on real-world customer examples. In this slide, the solution is relatively simple. We retrofit sensors to all of our machines on the shop floor, and that in turn feeds data back into our AI model. It can read things like machine stops, vibrations, and much more to help us decide when a machine is approaching breakdown or when a machine is most likely to need maintenance. And by being proactive, we reduce the amount of production issues, therefore saving money. We detect problems earlier, so we reduce our downtime and hopefully lower our scrap rate. Those same sensors could also be used to optimize energy usage. So we could track energy and machine energy usage across multiple process levels. We could flag furnaces that perhaps are holding temperature unnecessarily. We could benchmark the energy cost per part, so we could use that to be more effective in our quoting processes in the future. And by doing all of this, we hopefully save a bit of money, but we also demonstrate, particularly to our OEM clients, that we are taking sustainability seriously. The final example I will show is an example using simulation data. So all of these simulation runs that you're doing, how we might use this. Now, I must apologize, the video is rather quick. We will make this available or happy to discuss this with anyone after the session, but hopefully I'll try and narrate over it. What we're seeing here, and Tim will most likely show you this, is all we're doing here is creating a simulation, just like you would in any piece of simulation software. So in this example, all we're doing is getting some results. Then what we're going to do is create a particular project, because what we want to do is train a model on the simulation data. So what we're doing here is actually inputting some simulation runs to start training the model. So data's important here. Once we've done this, we can start to validate that model against some of the test data that we've got. And then next time we create a design, we're able to leverage AI and the test data that it's got to start making predictions for us. So the value of that really is that, number one, we start to use our simulation data. We start to feed it into an AI model. So again, if someone leaves the business, perhaps that knowledge is not lost. The AI model has got it. But also, if you're doing lots of different iterations of quite similar methods, perhaps they're products with slightly different dimensions, then if we train AI on it, we can often get answers very quickly without necessarily having to wait and run simulations all the time. So it certainly doesn't replace running simulations, but it certainly gives us some very quick insight before we even click that run button, which is very valuable in terms of reducing simulation time. So I hope you found that interesting. I mean, obviously AI is harder to demonstrate really, because essentially it's just making sense of data. But before...
Thanks for the introduction, Rob, and thanks once again, everyone, for joining us today. So over the next 25 or 30 minutes or so, we're going to be going through a workflow from sort of validation and testing of a component, showing the power of our rapid solvers. We're then going to optimize the part and hopefully achieve some weight savings while maintaining performance characteristics. And finally, we'll then take this into method development and create a method to manufacture defect-free casting. Today, we're going to be looking at an ATV steering knuckle. It's a fairly straightforward example, but we'll show you the process and get you thinking and maybe taking a look at some of the parts that you cast and allow you to ask some questions. You know, do you see parts that are over-engineered? Could we add value or additional services by offering to work with your customers on projects optimizing the parts, either potentially improving performance and also maybe reducing material usage as well? So as mentioned, we're going to be looking at an ATV sort of steering knuckle. In its current form, it's over-engineered, heavy, and to be fair, a waste of material. But to start with, we need to establish a baseline. Normally in traditional FEA, this can take time, but we are going to be using our SimSolid sort of rapid solvers, which is a completely meshless solver. And you'll see going from sort of import or start to finish of actually getting some results, this is going to take less than 5 minutes. So first of all, what I'm going to do is I'm actually going to start in my geometry tab. So also Inspire's like, a fully capable tool. I'm not going to be able to go through everything at the moment. We're just in the structures profile here, but we will be going into the cast profile. But there are many other profiles depending on things you do. But we're going to start in the geometry tab. I'm actually going to use my partition tool. So I'm going to use the partition tool, and this finds all these holes and features in the model. And I'm going to hit the tick box and I'm going to specify 4 mil here, and I'm going to accept that. And what you can see is this just basically partition these areas. What this means is for the actual optimization, I will be able to, it won't remove material from these areas. So everything else becomes what we call design space. So it will be able to remove material from these areas, but obviously crucial areas, obviously where we've got loads, forces, and obviously features being applied. You know, I don't want to start removing material from a hole that is obviously crucial to the performance of the part. So that's the first step. Then we're going to go into our structure tab. And second step is I'm actually going to apply a material. So I'm going to box select everything, all my solids, right click, go to material, and just specify A356 or 42100. You can do this via the materials tab. You can add your own materials. You can create materials, all that sort of stuff as well. Now I'm going to start applying some supports. So I'm going to just apply some supports to these cylindrical holes on the model. And I'm going to accept that, and then I'm going to click on these supports, and they're not fully constrained. I'm actually going to allow them to sort of move in this direction, so they are able to rotate around these areas. And then I'm going to apply some forces. So these forces are going to be simulate some sort of standard driving forces. We've got things like braking, bumps, cornering. I'm going to have 4 load cases simulating each of these actions. So I'm going to start with, and also first, before I do that, I'm actually going to set up my load cases. So this is load case 2. Those are the supports that are used in it. This is load case 3. They're all using the same supports. And load case 4. So I've got my 4 load cases created, and then I'm going to apply some forces. So we're going to add some sort of torque force, and I'm going to change my units down here to meters for the purpose of this. I'm going to change this to 400 meters, and I'm going to apply maybe a braking force in the Y direction, and maybe we'll have that at 2000. We can apply some sort of cornering forces. Maybe that's in the Z direction. I'll apply that at 3000. And I'm also going to apply another torque sort of force. I'm going to apply it in the rotating sort of Y area, and I'm going to just apply that as 100 Newton meters. This is just sort of simulating, maybe going over small bumps and things. So those are my sort of 4 forces created. What I'm going to do is just make sure they're all in the correct load cases. So I've got my torque 2 here. This should be in load case 4, which is correct. I'll put that one in load case 3. So make sure it's in load case 3. And force 1 will be in load case 2. And then torque 1, that'll be in load case 1. Okay, so we're pretty much actually ready to get some results now. So all I need to do now is go to my Analyze tool, click on this play button. This allows me to select which solver I'm interested in. So we've got SimSolid or OptiStruct. The load case I'm interested in studying. Literally hit the Run tool, and you'll see no contacts in the model. That's because I did this partition. I'll click Find and Run. That'll just designate bonded contacts to those areas. But you'll see literally within a few seconds, we'll literally have a completed solution. We'll get a green flag appear here, and we'll be able to open this green flag or click on the green flag and actually load our results. So you can see how quick that was in actually getting results. I'm not going to go through the results in too much detail today, just purely because we haven't got time. Obviously, you can see some of the result variable types that we've got: displacement, factor of safety, von Mises stress. We can see things like min-max. We can put call-outs on areas to understand the values. But the thing I'm going to be just focusing on today for the demo is a factor of safety. So we can see in this one, we've got a minimum of 13, and we can go through these and have a little look at them. But I'm looking at my results envelopes. This just allows me to see the minimum factor of safety in total. And we can see that we have got a minimum of 8, maximum of 2,500. And we can start to see where these are. So you can see actually it's on a sharp corner point. So in reality, we might not have a very, very sharp corner there. It might be rounded off. Probably the factor of safety might be a little bit higher. We could have added that and run another study on that. But we can see our factor of safety is 8. Motorsports, again, high performance motorsports, maybe let's say this part's 4. You might be looking at factors of safety of like maybe 2 to 2.5. For the purpose of this, let's say that we're going to try and meet a factor of safety of like 5 or 6. And that will allow us to meet our performance characteristics by still reducing weight. So those are our sort of results. We can go through those. If you're happy with them, you can sort of move on to the next step. Also, this part, obviously, we are looking to reduce weight. I think this part weighs around about 1 kilogram. So we can then move on to the optimization, which literally we're all set up for this because we've set up the FEA. We now can literally move straight into optimization. But before that, I actually want to set up some shape controls. So shape controls are great depending on how you're going to manufacture your part. So for our example, we're going to say that it's going to be a split draw, select a design space, and then you can specify your draw location. I'm going to choose that one, and I'm happy with that. So now that I've got some shape controls, depending on how you're going to manufacture it, if you're machining it, 3D printing it, extruding it, you've got different shape controls for that. Then I'm going to apply some symmetry as well. So I'm going to apply some symmetry, and I actually want the symmetry plane to be not that one, but this one. So it's symmetrical down the middle. So I've added my shape controls and my manufacturing constraints. Now I can move on to my optimization. And set up our basically our targets. So I'm going to use maximize stiffness, but we can use minimize frequency, minimize mass. We've got different types of topology optimization as well, what you can see here, but I'm going to stick to standard topology optimization. I want my mass target to be maybe 60% of the part, and you've got other constraints as well. We can apply thickness constraints. We've got porosity constraints. We've got different things obviously we can use. Obviously porosity constraints will be useful for casting, but for the purposes I'm going to specify none. We've got minimum factor of safety constraints, so I might want to specify a factor of safety of 5 or 6, and then specify the load cases you're interested in. We can turn on gravity as well, and then we can hit the run tool. No design space set, so that's what I was talking about earlier, the design space. This is an area where obviously the solver can remove material from. So I just want to right click on this solid here, specify as design space, and now we can see that's design space. Go into my Optimise tool and then click on the run. So this will start solving. For the purpose of obviously the demo, this isn't as meshless an instant. It does need to actually create a mesh, obviously, to get our results. This isn't an instant solver. So for the purpose of this, I'll just show you one that I did earlier. So I will show you the result now. So I'll just open another instance and take you into the result of this method. One thing, so this is what we can see here. One thing I just want to quickly touch on again is obviously porosity constraints. So here, obviously, we can specify a minimum safety factor, but this will take into account porosity constraints as well. So what this does, it doesn't eliminate porosity, but it actually reduces the stress in high porosity regions. So behind the scenes, it's basically doing a quick solidification analysis. Obviously, this allows us to see where last areas to solidify, thicker regions, and then it's then obviously optimizing the part around this and reducing the stress in the high porosity regions. This obviously the last thing you'd want if you do have any porosity in your part. You don't want it to be in high stress areas because that could then fundamentally weaken the part further. So that's just what the porosity constraint does. So let's show our optimized part now. So what we see here is the result of the software evaluating all load cases simultaneously. And this allows us to see where material is needed and where material isn't. At this point, we can use the automatic polyNURBS tool. So this fit polyNURBS tool. And I'll just press this now, or we can analyze the result. This will just create a validation simulation on the shape it is here. But I'm going to click the fit polyNURBS tool, and this will basically instantly smooth and wrap the shape if we wish. We can then actually manipulate and modify this within the software. You'll see one of the tabs along the top is a polyNURBS tab. This allows us to manipulate polyNURBS surfaces. If you were then happy with it, once you've manipulated it, you can then export that as a solid model in whatever format you wish. Alternatively, if you aren't sort of keen on the organic shape, sometimes you do get very organic shapes. Maybe that's not your preference. You can use the export this or do it within the software and export as STL and use it as a guide and reverse engineer in your preferred CAD tool or within Inspire, which is what I've done. So this is the polyNURBS shape. If you're not happy with this, obviously you can go into your polyNURBS tool as mentioned. We can play around using all these sort of tools, or you can use the shape as a guide and reverse engineer over it, which is what I've done. So I'll just show you that now. So we move on to here. So this is my reverse engineered shape. So this obviously used as a guide. I'm not going to show you that process because we just haven't got time, but it doesn't take too long. Hopefully you can see that there. But we do need to validate this. So I have already got this set up, so you can see exactly the way I had to set it up before. It's the same constraints, same forces and loads, but we need to validate it to make sure it does actually still meet the performance requirements. So literally, this one's already got results in it, so I can just hit that button there. you can start going through some of your results again. Look at different result types. I'm not going to go over these in too much detail, but the main thing that we were looking at for the purpose of this webinar is whether we meet sort of the factor of safety requirements that we were after. So I'm going to specify the results envelope, go to factor of safety, and we can see here minimum 7.9. You can see I've got actually some small radiuses on this one, so that might have helped. But we can see we've got minimum factor of safety of 7.9. I think before we had a factor of safety of 8, so slightly less, but obviously we've reduced the mass by quite a decent amount and still matching the performance characteristics that we need. So you might even say still over-engineered a bit, still room for improvement, still room for mass reduction. So that's just showing that we validated our model. It still meets the performance requirements, but that's stage 1 complete. Now stage 1 complete. Now we can move into obviously manufacturing validation. Obviously, this is where your knowledge is crucial, and where partnerships can be formed with your customers on projects, because it's all well and good the optimization spitting out a final shape, but this is where you will know if that part can actually be cast or whether it's going to be very, very challenging to cast. So that's where your knowledge comes in crucial, and as I say, partnerships potentially can be formed with customers or partners. So let's move into the cast profile. So within sort of one click, we're seamlessly sort of in the Inspire cast program now. So hopefully you can see here that we've got a few different tabs along the top. Still got our sketching tools, our geometry tools, and other modeling tools. But now we have our casting tab, and obviously this is where we set up and explore our results from our casting simulation and our method engineering. Workflow in this tool is left to right, so you start from the left and you work to the right hand side. But first of all, I'm actually going to use a geometry tool again. We did briefly look at that partition tool earlier, but I'm going to use one of my simplify tools now. So simplify, we've got a number of tools to potentially defeature your model, but one tool I'm going to use is the plug tool, and I'm going to plug or remove, so basically fill in or remove all these holes except that center bore, and hit this button here, and we can see those holes have been filled in. One thing I actually need to do following that is just use our Boolean tool, because actually these are all separate solids at the moment. I'll just box select all these, remove the imprints, and now that becomes all one piece. So the reason I've filled in those holes is obviously they are crucial, but we are going to machine them out afterwards. Obviously, they might be to high tolerance, and potentially if I cast them, it might cause some issues, maybe thermal hotspots, fluid turbulence, and potentially core pinning issues. So now onto the method development, and what makes Inspire Cast such a great tool is its simplicity and accessibility. All the clever stuff is sort of done behind the scenes, meaning you get a really clean user experience with straightforward workflows. And again, we haven't got loads of time to go through true full method development, but it might look something along these lines here. So in our casting tab, as I said before, its first step is to designate the cast part. So we can click on this tool here, choose our material, and then specify a pouring temperature. If we click this button, this takes us into our material database. We can see all the different standards, and we can see all our properties, and we can create and export materials and modify these properties if needed. I'm going to accept that. The next thing I need to do is just check that gravity is in the right direction. I'm happy with that direction for gravity, so I'll accept that. And then we also have a part analysis tool. So this is a great tool for quickly checking things like mold opening direction, so we can see if any surfaces haven't got any draft angle added to it, so we can see that might cause us some problems. So obviously I have forgot to add draft angle to these areas, but that's something I'd probably want to look at if I actually was going to go ahead and create a mold for this. We've got a fillet radius tool, obviously allows you to check the fillet radius, critical areas, thickness tool. So you can just literally click this tool here and it will give you a thickness analysis, and it will tell you your thin and thick regions. I'll just change my units to millimeters. So we can see our thinnest region and our thickest region, and you can see these color schemed, color map there. Also, we have a porosity preview tool. So if you click this, again, quite rapid, very quick porosity preview, gives you quick solidification analysis within a few seconds, which we'll see in a second. And this just allows us to see where we might get potential shrinkage. We can have a look at solid fractions, so we can see potentially how this part might solidify. Obviously, this isn't taking into account runners and any components, but it gives us an idea, obviously, of the areas that might be last to solidify, and that might guide us in terms of like component placing. So those are the things that we can look at there. We can also look at geomodulus. That might help with feeder size and stuff. So moving on to the next step, would go into the right hand side, but this part, obviously looking at this part, generally depending on volume and requirement, would either be most likely be high pressure if it's high volume, or gravity die cast if it's maybe a lower volume, maybe for motorsports, that sort of thing. To keep things simple, because we do have a limited time, and this will be a single part mold, and because most people on the webinar did select their main casting method as gravity, we will go with a gravity die cast method here. But note that all casting processes are included in the license. So we've got all our gravity casting. So in there we've got gravity die, gravity sand, investment, and also tilt pouring. We've got high pressure, and we've also got low pressure as well. So these are all our casting processes. So without having to go and design a full method, we can actually play around with gates and gating locations within the software to understand fill patterns. We can add components to see how these react, and we can run quick simulations using things like virtual molds, allowing us basically to speed up our method development. So so what we are going to do now is just show you an example of this. So I'm looking at this part. You might be looking at this part, thinking how are we going to fill this part? So you might go into your runner system and just create some gates initially, and trying to understand fill pattern and all that sort of thing. So let's use the gate tool. I'm going to look at it from the front here, and I'm just going to add some gates here. You can change the size of them, change the shape of them. Let's just change the size of them. You can compute flow tracing, move them around. I have them. If you're filling and then you're filling from a different area at different times, you can do all that sort of stuff. So I'm just going to create, let's say, 4 gates along here, and just very quickly knock those up so we can see these gates added. The injection point's already been added, so you can see these are the injection points. Obviously, this is where material's flowing in, so that's what that tool does. We haven't obviously got a full runner, so we haven't got a full runner filling system yet, so we don't need to use that tool. Moving on to the right hand side, this is where we can create or designate any casting components. So you can see we've got that porosity reviewer that we just looked at previously. Obviously that might guide us in terms of where we might want to add some of these components, but you can see we can add things like cores, risers, sleeves, all your different types of casting components, and we have the option to either create them in the software or designate them if you have modeled them up in any other software. For the purpose of this, let's just say I'm going to add a riser, and we can add it. Let's say we're going to add it just here. Again, we can modify these. This is obviously our modulus value, which we could have got from that porosity preview. We can modify our neck diameter, or this sort of thing, or we can use our tools to move the neck down and all that sort of stuff. This is just really a virtual riser or feeder at the moment, so it's just being used to get an idea of what might happen if it was placed there. Then we can move into the next step, which is setup. So we've got different types of setup. Basic setup's really good, again, for just getting a quick feel. This is obviously, we can choose filling time or initial velocity. Really, obviously, if we, for gravity die, you might have a certain velocity that you want sort of material entering the gate, and you might use that. So that might be like 0.4 or 0.4 meters per second. So I can set 400 for that. And that'll estimate the filling time it might take based on obviously the volume of the part and all the other variables. So you can see that roughly will take 2.5 seconds or so. If we want to go into a bit more detail, we can specify gravity casting, and we can specify constant liquid level on a sprue if you're maintaining the pour, spoon height, flow rate, tilt pouring, and investment casting as well. But we're going to just, obviously this is method development, so this is going to be, quick, dirty, understanding flow, understanding gate positions. So we can then move on and click the Analyze tool, and here we can specify the type of solutions that we want to study. So we want to do filling and solidification. We can specify when our part's going to be opened. Then with meshing, here I've got options to specify my mesh size or do a faster or more accurate. And then we've got different strategies. So I'm going to specify congruent, but you've got different strategies depending on your geometry. You might use one strategy over another. So these are all your different meshing strategies. Other stuff here, component mesh factors, we've got calculations, and we've got advanced. I'm going to run this without a mold. I'm going to say my mold is maybe 250 degrees, specify the material, which is just standard tool steel, and then we can actually run this part and have a look at some results that we get. So again, we don't get results within a few seconds. It will be quick, but it won't be it won't be instantaneous like we saw with the FEA, unfortunately. But you do have to wait for your results. So it meshes, then it will go into the filling stage, then the solidification stage, and then the demolding stage. And that's where we get all the stuff. So again, I will now show you sort of one I did earlier. And we can have a look at some results within Inspire Cast based on those. I'm aware that I've only got about 5 or 6 minutes, so I'm going to have to sort of fly through this. So now we can load the results, and we can start looking at our results. So we've got different stages. In the filling stage, we can obviously look at our fill pattern. We can see down here how long it takes to fill. We can obviously animate that fill as well and see if we get a nice sort of laminar, sort of smooth fill. So I'll just play that, and we can see the part sort of filling over those 3 seconds. Other results that we can look at in the filling stage. I'm not going to be able to go through all the results, just haven't got enough time. But obviously, for certain things, you might be interested in like last air. As I mentioned before, you might be interested in obviously velocities and what speed things are entering the mold. Mold erosion, we've got cold shuts, fronts of material meetings, all that sort of stuff you'd expect to see in here. That's all in there. Again, we've got our solidification stage, and this is the solidification stage. We can look at temperature evolution, we can look at solid fraction, so we can start to see last areas to solidify, potential break-offs where we might obviously potentially see porosity, and then we have our demolding stage, and here we can look for results like porosity and total shrinkage volume, and other results as well, which you'll be probably familiar with. Obviously, this one wasn't meant to be perfect, so we could show you some defects. Again, loads of result types, but as a method engineer, you'll go through like a few different designs until you get to your final one. Obviously, the one we've just shown wasn't great. With virtual gates, we can force the metal to enter. Obviously, with the virtual gates, we can force the metal to enter the gates at our designated velocity. But using our knowledge, we may have run a method with a full filling system and seen this, but it's very rare for the metal to distribute evenly, which might create unequal filling velocities and like a sort of a non-laminar fill. So because of this, obviously, let's pretend I've been method developing this, I've decided to fill from the other end and force a more sort of balanced fill and a fluid front that will sort of converge around that center core. Due to time constraints, as I say, we're literally going to have to sort of skip to the final method setup and show you how we do this. So if I just open the model, you might import your model. You might have CAD'd something up either within the Inspire software or in a CAD tool that you use, and this would be the setup. So again, left to right sort of workflow. Select your cast parts. We'll go AC 4200, 42100. This time we have got a runner system. Let's designate that, and we also want to create a gate. Let's obviously just modify the the size of that, and obviously this is sort of simulating pouring from a ladle as such. Then we can move on to components. We can specify that we've got here 2 risers or feeders, obviously a number of other components we could create or designate. In this instance, you might go, actually, I'm going to create, I don't know, some 2 chills and just whack these here, obviously modify the material, modify the temperatures, whack some chills on. And we also want to create a mold. So tool steel, temperature, different things as well. So we can add coatings and all that sort of stuff, but I'm going to bring that mold down to the top level. Accept this. Then we can go into our process setups. So gravity process, in this instance, we can specify a number of different things as we looked at before. I might specify spoon height in this instance, and specify a 50 mil. If you are doing investment, you can click investment, and we can create shell molds and all that sort of stuff. And the same for high pressure and low pressure. We can create casting components like shot sleeves and multi stalks for low pressure as well. We've got a mold in this instance. Now I want to obviously analyze this, and I can go into stage. I'm going to run solidification. I'm also going to compute deformation and perform trimming. This allows me to get my results like residual stresses. Again, I can use cycling if I want to. Going into my meshing, this time you might run this at a more accurate mesh, obviously a smaller element size. Specify your strategy for your meshing. If you want different component mesh factors for different things, you can do. And then we've got also options to select things like air exits and stuff if we've got venting and all that. We're going to then click the run tool. Again, I'm flying through this. Sorry, guys. It's just we are short of time, and we obviously do want to allow some time for questions. But we'd run through this again, go through the setup, and then, as I did before, I'll just show you the results, and hopefully we'll see a sort of a defect-free casting in a second. So these are my loaded results now. I'll just turn those back on. I am literally sort of out of time, so I'm going to have to wrap this up sort of very quickly and pass back to Rob so we can actually answer any questions of yours. I don't want to take up too much of your time, but we can start to look at some result types here. Obviously, we are simulating now with a mold, so we can look at other result types, mold erosion, mold temperatures, all those sort of things. Obviously, again, this is the filling pattern now. We can look at velocities, temperature evolution as it fills. One thing we did here, obviously, if we look at our porosity, we hopefully will see that all the porosity now is in the risers, which is why we wanted it. And if we go to our trimming, we can also see, or in the demolding stage, we can then look at things like residual stresses in the parts as well. So if I look now, we can look at our residual stresses in the part, and we can look at max locations. Obviously, we can put call outs and things, and we could go full circle if we wanted to. So we could actually map these results back into FEA, and then do a final validation taking into account your residual stresses in your parts as well. So we can go full circle. I'm out of time, but one last thing, we can obviously create reports and things on any result types. But I'm out of time, but I've just shown how we can go from sort of a raw CAD block to an optimized shape. We verified it and ensured that it was actually a manufacturable component, all sort of seamlessly within this Inspire ecosystem. We have really just scratched the surface on the software and only shown sort of one method relating to gravity die casting. But if you do want to see your casting process or the software in more detail, we can obviously set up more tailored sessions, and obviously speak about more about AI and that sort of thing as well. I will now pass you back to Rob, and now we can close up the session and answer any questions that have been sent in. But thank you.
Thanks for doing that, Tim. I'll just pop my camera back on. So yeah, I forced him to squeeze that into quite a short space of time. We've done a lot of these webinars focused, very much on that method development workflow, and what we've tried to do throughout this session is, I guess, to expand the horizon in terms of what we're talking about here. So we're trying to touch upon things like AI, things like optimization and FEA as well. So hopefully that's not been too quick, and it was a nice enough pace for you to get a high level flavour of what we can offer. We didn't bother with too many boring slides around licensing model and what's included and what's not. All you need to know is that the licensing model is cloud-based and token-based. And what that really means for an organization is there's lots of tools within the portfolio that you can use as and when you need to. So being able to dip in and out of optimization or FEA, even looking at things like 3D printing of molds, that's all in there. And obviously starting to think about AI use cases as well. So there's lots of things that we could obviously talk about in another session. But the main thing was that, you know, from our perspective, as I said right at the start, everyone already does simulation now, and I think it's more a case of now what else you can offer. Can you collaborate with organizations around their part design? Seeing as you know how it could be cast, can you provide some advice on helping them optimize that part, for an example, as an example? Or can we start using AI to improve our sort of internal operations, start building up a knowledge base or AI model based on all of the data that we're already capturing? So in terms of next steps, now is the time to put your questions in the chat if you've got any. So do put those in the chat. Just in terms of next steps, there's a couple of things that we can do for you. As Tim mentioned, more demonstrations. Obviously, some of you will be on the call that have different casting methods entirely. We can talk about that. Some of you might be happy with your casting simulation software and have actually joined more to talk or learn a bit more about AI. That's fine as well. So we can do a more detailed discussion / demonstration based on what you might want. And we can also, of course, provide trials for the solutions. Obviously, it's a bit harder to do that with AI-based tools, but certainly the optimization tools, FEA tools, casting simulation tools, we can provide access to those for you to have a go. And of course, share examples of customers that might have moved away from more expensive software for business case support and all that sort of thing. So Tim, just pop that poll up for me if you don't mind. This one will remain private. We won't share the answers to this, but we're just trying to understand whether you would like any more information from us. Perhaps we've bored you and you don't want anything, so just put nothing for now. But perhaps you want to understand a bit more about costs, or perhaps there's something that we've covered that you just want a bit more information on. So we'll just allow you to fill those out and just have a look at some of the questions. So one of them, Tim, I'll let you answer this one. They're just talking about can this software be used, I guess, by non-simulation experts? So the specific question: can our method engineers use this day to day without being a simulation specialist? So Tim, do you want to answer that one?
On your mic. So yeah, good question. I think hopefully you saw by the demo that like it is a very easy to use solution. I mean, Inspire Cast is basically built for method engineers. You know, the setup's quite guided. You don't need to worry too much about your meshing and that configuration. So yeah, I'd say, you know, most engineers can basically get up and running with Inspire Cast and some of the Altair solution in general within sort of like a day of either just using it and having a few demonstrations, or within like a day's training, basically.
Okay. Next one. Yeah, I mean, this question, we don't really have a team for AI, and is AI accessible to us? Obviously, in the presentation, we were giving sort of examples of putting sensors on machines and feeding that to AI models and all of that sort of stuff. It can be, quite a bit simpler. Most of you will be keeping records of scrap, for example, and probably linking that across to a part number or maybe even the machine that caused it. So even that digitized could help you answer important questions by feeding all of that data in. And we haven't really talked about it, but Rapid Miner is a tool which is designed for engineers, not data scientists. So the ability to sort of manipulate data from multiple sources and feed that in to an AI model to make sense of it. So you can just start small. You can pick the one thing that would give you the most value without necessarily having to change absolutely everything. So you certainly can start with it. The next question. Yeah, there was a quick video that we ran, which was on using physics AI, which was learning from the simulations that they've done. And there's just a question here, Tim, on how much data we're actually going to need to start making this useful. And I guess what sort of use cases this might apply to or be useful for. So I'll just quickly mute myself, Tim, and let you answer that one.
Yeah. So yeah, physics AI. Obviously, this was the demonstration of basically training your AI model with your own simulation data, and then what actually effect this sort of has. And so obviously, once you've trained your model, you get your results within seconds rather than sort of hours. So you can speed up your simulation time very, very rapidly. But obviously, everyone asks, well, what does it require? So it's using like geometric deep learning, and obviously this basically looks at the sort of the underlying sort of shape and like features rather than like variables. So you don't need like millions and millions of data points. Like typically, like feeding the system, the model, between 10 to 30 sort of historical simulation sort of runs. That would be enough to start making predictions basically. It's great for if you are producing parts that are sort of similar. So if you're like working and doing a lot of automotive parts, maybe an example like steering bracket, or to show if you're doing a lot of those similar parts, you can start feeding your data this. But yeah, it's enough. I'd say 10 methods to sort of start training your model with to make like reliable predictions. And that obviously that can save, but then going down the line that can save you sort of like hours and days worth of actual simulation time. So yeah, hopefully that gives you a bit of an idea of where you can use it and how long it sort of takes.
Thanks, Tim. We're out of time. Someone did ask for my email address just in the chat, so I've just put up our details anyway, just in case you did want to email us. If it's sort of more casting technical related, Tim's probably your best contact. If it's more about costings or perhaps AI use cases, I can help with that, or just email both of us. We will follow up with you all after, interested to see what you think of the content. So expect an email or call. But apart from that, we are out of time. We will get a recording sent out to you as well, so you can share that with colleagues. But all that's left to do is thank you very much for attending. We appreciate your time, and we'll be in touch. Thanks very much.